Everyone knows the compound on this lathe is a weak point, which is why I deleted it, but I need it for an upcoming project, so let's see if we can make a better clamping system and improve its rigidity. Welcome back to Cloud42, I'm James. Last year, I deleted the compound on my Grizzly G0602 lathe and replaced it with a solid cast riser block. That riser block has turned out to be the third best upgrade I've made to the machine, and I would do it again in a heartbeat. However, I have a project coming up that will require me to cut a short taper, and for that, I'm going to need the compound. So this seems like as good a time as any to address the totally inadequate clamping system that it comes with from the factory. Let me pull the solid tool post riser off of here and see if I can demonstrate the issues with the stock compound. Now, this solid tool post riser block has been great, but as I said, it doesn't help very much when I need to cut a taper. The stock compound is held on with two studs in these two center holes. The other holes I put in for the solid riser. And with nuts on top of this, those two posts are the only thing resisting the tipping forces on the compound as it enters a cut. And the whole thing is just held down with this steel clamp. Now the base of this is held on with 3 M6 screws. That could probably also be improved. We'll see if that ends up being the weak point, but the clamp is definitely a weak point. Now the screw-on base is actually marked with the graduations for setting the approximate angle for the compound, so I'll need to make sure that goes back on clocked in the right position. And with that out of the way, it's possible to see just how weak this clamp is, especially up here at the front where the window is for the graduations to show through. There's just so little material in there that this thing flexes. When the tool enters a cut, you can see the front end dive and you can actually see the base flexing and allowing the compound to move. So my goal here is going to be to use these additional 4 screw holes that I put in for the solid tool post riser and make a much beefier clamp that has more cross-sectional area and will hold up better under heavy loads. As luck would have it, I already have a 3D model in Fusion 360 of the cross slide of the lathe that I used when I designed the solid tool post riser. So I can just isolate that and use it as my starting point, and it already has the 6 holes in the correct positions where they're already located in the cross slide on my lathe. I want to just go ahead and use those same holes in the same pattern. It would be possible to put in some different holes, but I already have them there, and so I just want to go ahead and use them. And actually, yes, I was planning ahead for this project when I decided exactly where I wanted them for the solid tool post riser. Now, I didn't want to model the entire compound, so I just modeled the base. This isn't exactly the same dimensions as the actual base part of the compound. It's actually a little bit taller, and I did that so that the height of this part would reflect the distance up to the underside of the compound, just so that I would have a reference and I could judge clearances. Then I designed the largest, beefiest clamp that I could fit into the space available. So I've got some reliefs cut in the sides for the nuts and washers so they'll clear the underside of the compound. And you can see, just judging from that top surface, that there should be enough clearance to get a wrench in there and tighten this down. My goal here with this design was just to get as much cross-sectional area in the part as I possibly could. If you look at a cutaway here, you can see that there's actually quite a bit of material under the nuts and washers on the studs. That should provide quite a bit of rigidity and a nice beefy connection and extra thick material across the front and the back that should get good clamping pressure all the way around on the compound base. And then in the front, where I have the window here so that you can read the graduations on the front of the compound base, you can see there is a lot more cross-section area than there was in the original part, so it should have a lot more rigidity than stock. Now I think everything here is going to fit, just judging based on the model and the dimensions that I have. I think everything is going to be fine and we're going to have plenty of clearance. But to be sure, I'm going to make a 3D printed part and test it first. I'll just go ahead and print this in PLA. Should be nice and simple and quick, and then I can take that part out to the shop and assemble it and make sure everything is going to work. Doesn't have to be strong enough to survive. It doesn't have to stand up to actual use. It's just a test of the dimensions. Now I'm assuming everything's going to fit, so I went ahead and made a drawing with all of the critical dimensions, and once I've test fit the 3D printed part, I have everything I need here to make one out of steel. And of course, if it doesn't fit, I can just adjust the model, the drawing will automatically update, and I should be good to go. And by the way, if you want to make one of these for yourself, the drawing and the 3D models will be available on Patreon. Of course, you could also just screenshot the video and everything you need is right here. Got the 3D printed part right off the printer and it turned out great. I did use the breakaway support material for the interface for the support underneath, so that came away nice and clean. And we'll just mock this up with the compound base. Set it on here and get some studs in. Now there is a small gap between the clamp and the cross slide around the edges, and that's exactly what we need so that we can get a little bit of clamping force, putting the 6 studs and the 6 washers and the 6 nuts. Now this setup is going to have a lot more hardware and it's going to take more time to change the compound angle, but hopefully the rigidity will be worth it. And yes, we can definitely read the graduations through the window, so that's going to work too. Let me go ahead and put the compound on to make sure we have the clearance, and unfortunately the pin's not lining up just because there's some play in the system and I don't have it clamped in exactly the right place. Get that lined up so this will drop down, and it looks like we are going to clear the nuts just fine. I think this is going to work. Let's go make one out of steel. I'm going to make the clamp out of a 3/4 inch thick piece of hot rolled mild steel. And the first thing we need to do is square up the block and bring it to dimension. Now none of the sides of this thing are square or necessarily even flat. So I'm clamping with a piece of aluminum TIG wire to take up the differences in the saw cut and tamping it down securely on the parallels. Now to clean up the large flat edges, I'm using the Tormach Superfly, and this is with their steel specific insert. And I actually had a lot of trouble with chatter on this tool. I realized later that my problem was probably the angle of the bar in the fly cutter. It needs to be tilted down slightly so that the leading corner of the insert does all the cutting, and I had it tilted up a little bit so the entire bottom flat edge was engaged, and I think that was the problem. I'll make some adjustments next time I use it. But in the end, I got a reasonable surface finish, flipped it over, and brought the piece to the correct thickness. Then for the long edges, I'm using a 1-inch diameter insert end mill to clean this up. I believe this one's from Shar's, and it just did a beautiful job. Left a really nice clean surface finish, deburred it, flipped it over, and brought the part to width. And then for the short ends, I put in a corncob roughing end mill and took off the mill scale and brought it down close to the dimension, and then swapped out for a finishing carbide end mill to put a nice surface finish on the edge. Now with the block all squared up and brought to the correct dimensions, we just need to find the center. So I'm using an edge finder with the half function in the DRO to find the center in X and Y. And then I'll just drive the mill to 0, 0 and visually confirm that that looks sane. And it does. To rough out the shoulders, I'll switch back to the roughing end mill. And then I want to take a quick measurement and see exactly where I ended up on thickness. I'll do a little bit of math and write down my target dimensions on the mill vise with a Sharpie so I don't screw them up. At least so I don't screw them up by forgetting what they're supposed to be. To establish my 0, I'll just bring the quill down and touch the workpiece, 0 everything, then I'll lower the knee a couple thou so I don't chip the cutter, pull it off the side, and then raise the knee for my depth of cut. Now I'm going to take the whole 208 thousandths minus about 5 thou for a finishing pass. We'll go the full width of the cutter and just plow it through. I am doing this in the conventional direction just to make sure I don't have any problems with it grabbing and breaking the cutter. This mill is pretty new and it's pretty tight, so it shouldn't be an issue, but this is the safest way to do it. Take each side in a couple of passes, and I'm staying on the width about 5 thou off of my line as well. And then we'll switch back to the finish end mill, touch off in the same way, and take some finish passes. We'll take the remaining 5 thou off the floor, do both sides and then come around, and on the second pass we'll take the remaining 5 thou off the wall as well, so we get a nice clean surface finish on both sides. Now that should be it for the milling. Now we need to put some holes in it, so we'll switch to the drill chuck. When I drill holes, I almost always start with a 120-degree spotting drill, and I do this for a couple of reasons. The first is that it establishes a drill point for the larger drill to follow and helps to keep it from wandering. But the other is that I can see where the holes are before I've ruined the part, and I can do a sanity check just to make sure that everything looks like it's in the right place. The holes spotted, we'll switch over to the final drill size and just punch these through. These holes have plenty of slop in them. There's plenty of clearance for the studs, so the location isn't super important here, but it's just habit to do it this way, so I do it this way. We'll just go ahead and punch through the 6 holes for the studs. Now I am letting up the pressure periodically just to break the chip. It's not a full peck, I'm just, releasing the pressure so the chip breaks. And then I'm trying to be careful as it goes through the bottom of the hole just to make sure it doesn't grab and yank the part out of the vise. Now with those done, I'm going to pull out the drill chuck, and for the hole in the center, I could use a drill, but I want to use an annular cutter instead. So I have an R8 arbor that's specifically designed to hold these 3/4 inch shank annular cutters with 2 Weldon flats. We'll get that anchored down well, centered up, and we'll just punch a hole through the center. Now, this is the largest annular cutter I had at the time I machined this. I actually have a larger one now, but it didn't arrive until after I'd already filmed this video. So it's the biggest one I have. We'll just punch a hole through the center. We're going to end up enlarging it on the lathe, and the closer I can get to the final size here on the mill, the less time I'll spend making chips on the lathe. Just make sure and keep this lubricated well. This is a high-speed steel cutter, but I still don't want to abuse it. Just make sure the chips are not picking up any color. We'll just go through nice and easy, and because it's not removing all the material, it's only making an annular cut, it ends up being a lot more efficient anyway. The last feature we need to make here at the mill is the window so that we can see the graduations. And to make that, I'm just going to turn this upright in the mill vise. We'll use an edge finder to establish a 0 on the bottom of the part and the half function on the DRO to establish our center left and right. Now to remove the bulk of the material for this window, I'm going to use a 3/4 inch carbide insert end mill. And we'll just bring it in here on the center line, touch off, and then we'll plunge down to actually remove the material. And I'll just take this in small steps so that we don't load the mill up too much. And just work in until we get to the depth shown on the drawing. When we get close to the depth, I'll take just a few thou on the last pass, so we should get a nice, clean surface finish. Though it doesn't really matter because it'll be up underneath where you can't see it. But, as long as we're going to do it, we might as well do it well. Now to actually cut the chamfer, I do not have a chamfer bit large enough for this, so I'm going to use the boring head. And I was planning on actually grinding a 45-degree boring bar for this, and then I realized I don't have to do that because I have a 45-degree single flute countersink with a 1/2 inch shank, and I can just put that in the boring head and push this single edge off center to cut whatever size chamfer I want. Now, I'm not totally sure how this is going to work. I'll just push this over about that far, and we'll just take a cut and see what happens. This is just a high-speed steel tool. I'm going to use plenty of lubrication here just to make sure we don't chew it up, and we're going to take this nice and easy. I do have the quill locked and all the way up for maximum rigidity, and I'm doing all this work by raising the knee. And raising it slowly into the cut, it does seem to be doing a beautiful job. It's cutting nice and clean and quiet. Push it over a little further. And bring it out to our final dimension. And when I say dimension, I mean I'll just bring it out till it looks about right. And that worked beautifully. I don't think I could have pushed it much further without chatter, but that looks great. Now we can take this over and finish it on the lathe. To bore the center hole and the shoulder out to the correct dimensions, I'm going to hold this in the 4-jaw chuck because it's square. And I'm going to use copper pads to avoid marring the surface finish. Now, honestly, I don't care, but lots of people do, and having some little strips of copper around to keep the chuck jaws from actually cutting into the part are a good idea, especially on the 4-jaw where you're going to be pushing it around and the jaws are going to be scraping on the surface. So I'll just get this in approximately the right position with copper under all of the jaws, and then set up a dial indicator and use this central bore to try to get it centered. Now, this is not going to be perfect because this was cut with an angular cutter and the surface is rough and, you know, it might have wandered a little bit. It's hard to say, but it will be good enough for this application. That's within about 1 thou, so I'll move the dial indicator and check the face. And of course, this is an interrupted cut or an interrupted reading because we're going over that gap. But I'll just tap it in and get it so that it's running as parallel as I can. And that's within 1 thou, and because we moved it around, we're going to have to go back to the center bore, and that's off a little bit, and we'll get that dialed in. Well, that's running within 1 thou, total indicated runout. That is good enough for this part. Now I'm just going to grab a carbide boring bar and open up this hole to the required dimension. I'm going to start out with a really nice light cut, and this lathe is just handling that beautifully. You can see the chips are coming off nice and clean, no color, but that's going to take forever, so I'm going to push it. And you can see as I push this harder, the chips are coming off blue. They are breaking, but they are also going all over the shop, and they are hot. I've got burns all over my hands. These things were stuck in my hair. It was not a great experience. As many of you are aware, back in 1997, the World Trade Organization defined any camera that could record video clips of 30 minutes or longer as a video camera, subject to higher tariff rates. And that's why many cameras stop recording at 29 minutes and 29 seconds. And that's why I lost the rest of this clip. Fortunately, I was able to do a dramatic reenactment after the fact. I saved just a couple thou for the last pass on the diameter, and then in one motion took it all the way to the correct depth, and then wound the slide in to clean up the shoulder and leave a nice surface finish. Then I came back with a chamfering tool and just cleaned up the edges. I wasn't really trying to put a chamfer on these. I just wanted to soften them so that they wouldn't cut me as I handled the part. And then to clean up the back side of the bore, I used a threading bar and reached through and just took the burr off of the inside. And that should be the part complete. Do a little test fit here just to make sure the shoulder's the right depth, and it looks like we've got a few thou there for clamping, so I think that is going to work. Be careful here not to lose my copper strips. Throw those back in the box and I'll use those next time. Now, unfortunately, you have to actually assemble the clamp into the compound, so we'll slide that on, put the base on, and drop in the 3 M6 screws. Now, I think this is probably now going to become the weak point on this lathe, so I could easily come back and put in 3 more holes and increase this to 6 fasteners. I'm going to run it like this first and just see how it works before I go to the trouble of doing that, but that's probably the next thing I'm going to need to do here. I'll put some gronk on these, actually stretch the fasteners a little bit just to get the best rigidity we can. Make sure everything is clean and assemble it. Now with 6 fasteners instead of 2, this does take more time, but I think the rigidity improvement is going to be worth it. Now I'll just go around and tighten these all down gradually a little bit at a time so we don't tilt the clamp left or right, or lift one side or bend it unnecessarily. I'd like a nice, firm, even clamping pressure all the way around. And this is pulling up nice and solid. I'm I like the feel of this. You can really feel the difference between this and the original clamp. Now, putting a little bit of pressure on this, I'm actually lifting the cross slide. I think that gib's a little bit loose. I probably need to pay some attention to that. But the compound clamp looks nice and solid. Let me go ahead and put the Aloris tool post back on here. Now, I could go make all the parts to put the multi-fix on here, but I don't think I'm going to use this very much, so I'm probably not going to bother spending any time on that. Now, rest assured, the solid tool post riser is not going anywhere. This is going to be on the lathe most of the time, but I will swap it out when I need the compound for a specific operation. Otherwise, the solid tool post is a really big improvement on this lathe.
People tell me I should just buy a better lathe, but where's the fun in that? If you enjoyed this video or found it useful, give it a thumbs up, subscribe, and maybe consider supporting the channel over on Patreon. If you're already a patron, thank you. You make it possible for me to do this. Thank you for watching.